Okay, so today I'm talking about chapter 8.2, the wave nature of light. Okay, so light can be described as coming in waves, like it acts like a wave. So when there's light coming in waves, two light waves can come together and form a light wave with a larger amplitude. So the two small light waves come together and they're in phase. If they're in phase, it'll get larger. But if they're out of phase, it becomes flat. The wave. Okay. Okay, and then there's these different variables to describe light. Like here, V means frequency is equal to c, which is the speed of light here, divided by wavelength. Uh, so here's a common unit, a nanometer, exponent to the negative 9, scientific notation, like in a billionth of a meter. Okay, so here's some, like I said, frequency times light speed divided by wavelength. So there's this constant that's called Planck's constant, which is used for calculating like the wavelength based off the frequency. So I can calculate the wavelength, basically calculate the wavelength in nanometers of the red light emitted by a barcode scanner that has a frequency of 4.62 e to the 14th in hertz. That's a frequency. So frequency is equal to c over an inverted v, which is wavelength. Frequency is equal to the speed of light over wavelength. So I had to solve an equation to get wavelength. So I multiply both sides by x, x being the inverted v. So I now have frequency times x is equal to the speed of light. And then, so I have the speed of light divided by the frequency gives me the speed of light divided by the frequency gives me the wavelength. But this is not yet a Planck's constant. This is how frequency and wavelength are related. So, talking about interference is called destructive interference if the two waves are out of phase, and it's called constructive interference if they are in phase. And here's an example. So these are some in phase waves, and that's constructive interference. These are some out of phase waves, and that's destructive interference. So if you got a light source or or electromagnetic, F, wave, like a radio wave or a light wave, and there's two slits, it will repropagate through the two slits into these waves like that. And then if they collide in phase, it'll make a bright light. But if they're out of phase, it would make like a dark light. So this is simple with the light. And it depends on the distance traveled, whether they're in phase or out of phase of the wave. That's a property of light. What is it else now? Okay, now I talk about Planck's constant. Planck's constant is used to calculate the energy in a given wavelength. Okay, it's usually an equation. According to Einstein, the amount of energy is a light packet depends on its frequency according to the following equation. E equals hv, where h is called Planck's constant, and it is 6.626 raised to the negative 34 exponential notation joules per second times the frequency. Frequency is equal to the speed of light divided by the wave. So here's another question. Nitrogen gas laser pulse with a wavelength contains 3.83 millijoules of energy. How many photons does it contain? So I multiply the speed of light times Planck constant divided by the wavelength in meters, and that gives me the energy of a photon. No. How many photons does it contain? No, how many photons does it contain? So here I got the energy of a photon. This is the energy of a photon. This is the energy of the whole laser beam. I divided that and got this. The amount of photons. Yeah.